Hi friends, in this video we'll discuss about quenching dynamic mesh plus lumped analysis. So on the left hand side you can see this is a water in which a hot steel ball is present. So we'll need to describe how the motion of the sphere would vary with respect to the time inside a water, and the hot sphere or the hot steel ball, how it emanates the heat into the water, as well as the total time it requires in order to come back to its atmospheric temperature. So we'll discuss about all those things in the simulation. Prior to going into simulation, we will discuss about buoyancy force effect, how it affects the motion of the steel sphere, as well as dynamic mesh, what exactly happens in the dynamic mesh, and a bit introduction about the lumped analysis. Uh, so now you can see a ball which is immersed inside the water has a weight in the down direction and force of buoyancy in the upward direction. So that net force is mg minus fb, where fb is the buoyancy force. It is density of the fluid into the volume of the fluid dispersed, which is nothing but the volume of the sphere. So it is 4/3 pi r cube. Radius of the sphere we have considered is 2 mm, and the density of the steel is 8030. So on applying all these things in the equations, we'll get F net is equals to 0.0022 n, which is nothing but net force. So we all know that net force is nothing but mass into acceleration. Acceleration is the rate of change of velocity. So now dv by dt is 8.26. So on applying the indefinite integral, we'll get v equals to 8.26 t plus c. In order to solve c, we will try to have the value of velocity at initial time. As we know, we have gently placed the sphere inside the water, there would be no initial velocity. So at t1 equals to 0, v1 also is equals to 0. So applying that to 8.26 t plus c, we'll get c is equals to 0. So the velocity is 8.26 t. This is the way how the sphere velocity changes with respect to time inside the water. Please do remember this. We'll try to apply in the simulation part. Now we'll get into the dynamic mesh. So dynamic mesh is nothing but mesh getting deformed. So in order to accommodate the deformation inside the mesh, there are two methods which we need to follow. One is smoothing, other one is remeshing. It is mainly meant for triangular elements in 2D or tetrahedron elements in 3D. So in the smoothing technique, we need to move these nodes to other positions, and in the remeshing, the quality is getting violated, then it will split into 2 or 3 elements in order to make the quality again into a good part or into the good condition. So there are two kinds of smoothing techniques. One is spring based smoothing and other one is Laplacian based smoothing. So in the spring based smoothing, we all know the spring energy equation, or spring force is nothing but k into x, where k is the spring constant and x is the deformation. So initially when it is in a static condition, when there is no extra force, what does it mean by that? So there is no imbalance in force. So in that condition, F is equals to 0, or F net is equals to 0. So when this ball moves in the down direction, then also there is no spring force or there is no extra force that would act on this system. So in that time also we need to bring back the force to be 0, even though the node position has been changed. So with respect to that, so there would be an iterative based technique in order to balance that force. This is the displacement of the nodes just beside the node which need to move, or the adjacent nodes with respect to which a node would move. So has this equation, it tries to iterate until we'll get a net force in the entire system as 0. So now delta xim plus 1 would be added to the initial position of the node to get the final position of the node for a single time step. So this is a spring based smoothing. But whereas in the Laplacian based smoothing, so in the Laplacian based smoothing, the position of the node will change in such a way that the mesh quality would improvise, or else it will not change. So that change here they've been calculating using an arithmetic mean of the all the positions of the nodes just beside the node which need to move. So this is the Laplacian based smoothing. And in the remeshing, we have a different criteria in order to remesh. One can be your skewness. If you mention a skewness and your after smoothing, if the value of that skewness is more than the mentioned value, then automatically it remeshes. And the minimum length scale, if after smoothing, if the minimum length scale what you have mentioned is getting violated, then also it remeshes. Now, if the maximum length scale, if it violates after smoothing, then also it remeshes. And if it doesn't meet the length scale that is specified, there is a height of that element, it doesn't meeting a specified length scale, then also it remeshes. So all this happens after smoothing only, after the node displacement only, or else remeshes. Remeshing is nothing to use. And other one is the face region remeshing method, in which the deforming region has some faces, right? So those faces will be remeshed in order to maintain the certain good quality elements. So these are the two conditions in order to have a mesh motion or a deforming mesh in a triangle or a tetrahedron for 2D and 3D. Last but not the least is a lumped analysis. So lumped analysis state that for a conductivity material, for high conductivity material, the temperature would be same in and out or in the entire volume when the Biot number is less than 0.1. So now you can see here the red hot balls where the temperature would be same along the entire volume. So because it is obeying the law what I have stated, HLC by K is a Biot number. So the value, if you calculate HLC by K, will be less than zero point 0.1 for these steel spheres. Then only the temperature would be same along the entire volume. We'll get into the simulation and we'll discuss. So this is the mesh which I have considered. It is very crude because I just want to uh, have the simulation run very fast, because it is a triangle simulation. It will take more amount of time. So it is very crude. You need to refine it in a very good fashion, or else the results what we will get will not be accurate enough. So as this is a demonstration purpose, I think this would be sufficient. So I have given all triangle methods. So right click on the mesh. So on right clicking you will get different options. So in that I have selected a method option. In that method I have selected two bodies, and to the two bodies I have given all triangle methods. And I went into body sizing, and for this body sizing I have given 1 e power minus 3 m or 1 m. And here I have given the element size for this as 5 e power minus 4. So this has a bit refined mesh when compared to this. So this has 1 e power minus 3, and in general the global sizing you have given 5 e power minus 4. So the sphere has bit refined mesh. And the inlets here named sections. So this is the topmost. I have named it using this edge. Right click. So select the edge. Right click. Create named sections. And on creating the named sections, I have named it as pressure outlet. Similarly, wall. Have selected by using control this one, this edge, and created wall. Similarly, have selected face and selected this face of sphere and have given a sphere as the name. Similarly, this has fluent. So now we will just go into the fluent. Just show you the setup. So this is the general setup. On clicking general, I have activated transient, and in the Y it is minus 9.81. Similarly, I have on the energy and viscosity as laminar. I have went into materials. I have went into create. I have went into database. I have loaded water liquid. After that, I have clicked copy, close. Right? I'll close this. And in the water liquid, I have selected density as bosonic approximation, and the density reference value is 998 kg per meter cube. And the remaining values have just left as it is. So it is 4182, 0.6. This cost is 0.001003, and thermal expansion coefficient dash 0.001. So we close it. Now I'll be going into the boundary conditions. In solid, in for you, just you need to go into the Fluent database, get into solid also, and select steel, copy, close. Similarly close. So it will have the steel also into the solid. Then go into cell zone conditions, click on this fluid, and change the material name to water liquid. Go on to solid, change the material name to steel instead of aluminum. The boundary conditions, outlet, click on that. So it's a pressure outlet with 0 gauge pressure. And thermal backflow temperature is 300. In the wall, you can leave all these as wall itself. You need not change anything. Now get into the dynamic mesh, activate smoothing and remeshing, and get to settings. So I've used the smoothing diffusion based, or you can use spring or laplation based, anything you can use. Go to remeshing. So just use spring because you have explained about spring. Go to remeshing, click on local cell, and you need to have these values. What are the values of minimum length scale, maximum length scale, and maximum skull skewness? So in smoothing, when the node has been changed to a position, if that position makes the element length less than this, then automatically it remeshes. If the length is more than this, automatically it remeshes. If the cell skewness is more than this, automatically remeshes. I'm asking it to remesh or check whether it was obeying all these three rules or not for each and every iteration. So one stand for how many iterations you need to check for. Okay. Next, get into create edit. So I think before going into create edit, we need to create a profile file. So the velocity of the sphere with respect to time. So I'll just show you the profile file so that you'll understand. So this is the profile file. Movement linear point 11 and 1. So you can check this. So these are the 11 points, and this is the time with respect to have a variation. So at 0 time, velocity is 0. As we mentioned in our presentation, you can see 8.260. So now you substitute here at t equal to 0, what is v? At t equals to 1, what is v? So I'm substituting all those things. I'll get different velocities at different times. My intention is have that variation of the velocity of the sphere with respect to time, and as soon as it touches the wall or the wall just here, the time or the velocity should become 0. That also I mentioned in this notepad. You can check at this time the velocity is becoming 0 and save that. Save it as .prof. You need to I'll just show you once again. File, save as. You need to save. I have saved as quen.prof. So we will get quen.text instead of txt. You save the extension of .prof. Then go to Fluent, file, read, profile. This is the thing. Just read it. So after reading, it will be present in your boundary conditions. You can check here the profiles. So this is the profile what I have created. Movement linear, which has two fields, time and velocity. And now I'll get to go dynamic mesh. So create edit. So this is the sphere. That is sphere contact target region is the solid. Fluid contact region is the fluid. And FFS surface shadow is the shadow that would be created for this sphere with respect to fluid, and this is the surface of the sphere. So when there is a contact between a solid and a fluid, a wall and wall shadow would be created. So in the dynamic meshing, so this wall and wall shadow also need to move with the sphere in order to accommodate the change in mesh or the change in volume or deforming. So just I'll just show you. So this is a rigid body. So keep the value as y in meters. So it is 0.017 what I have mentioned, or the position, initial position of the sphere. It is the center of gravity of the sphere with respect to axis you need to mention. So I have an axis at here at this position, and the sphere is initially at this position. So distance between that axis and the center of the sphere is x0, where y is 0.017. So it is not minus sign, it is 0.017. As it came here, it was showing that the value, but initially it is present on the topmost point, so it is 0.017. In the meshing options, you need to give the cell height, which is just inside the sphere and just outside the sphere. So inside the sphere and outside the sphere, the values of cell height is same value. So I have mentioned same value. If you want to just verify, you just need to go to mesh, click mesh, just zoom in, click on this node and check here. So you can check it is 0.305. I mean 5 into 10 power minus 4, and here also same. So now what the values are given is correct. So that you need to mention. Next, going to click on create, and after that glowing fluid surface shadow. Similarly mention the values of y. It is 0.017, because surface and surface shadow, or wall and wall shadow has both same center of gravity. Similarly, meshing options have these values. Click on create. Next, for fluid, have the remeshing and smoothing with the global settings as a deforming, and this should be deforming. Initially both are rigid, now this should be deforming. Click on create, and now for here also rigid body, go to rigid body, movement linear, the center of gravity location is same, it is 0.017. Click on create. So now the setup is completed. Maybe we can have report files or report monitors. I think it's not required for this case, but still, if you want to have, you can have. I'll just initialize this. Initialize. So after that, you need to patch the sphere. I'll patch the sphere with 1200 Kelvin, and I'll patch the water with 300 Kelvin. So this is a fluid. I'll patch it with 300 Kelvin patch. So now the temperature of the fluid entire is 300, and the sphere is 1200. Patch it. Now you can go run calculation, and time step size as 0.401 you can take, and the number of time steps as 5000. Click on calculate. So after the ball has came back to this position, so it will travel from this position to this position. We can just increase the time step size so that the simulation will be completed in much faster time, because we need not have the time step, low time step when it is reached here, because there is no dynamic meshing anymore. It is only the heat emanation, so it can have a higher time step size. So now I'll just click on calculate and we'll check. So I have run many steps, and this is the post processing. At time 0 seconds, I have activated the whole surface sphere. So it is at 1200 Kelvin, and water is at 300 Kelvin. So I'll just show you at the end of the time step. So the temperature is everything at 300 Kelvin. So that means the temperature has no change after these many time steps. It is becoming, or is equating to the atmospheric temperature. Now, meanwhile, how the temperature is getting varied, we'll check. We'll get to time step factor, and we'll just have this animation. You can just have the play. On the left hand side, you can see how the temperature is getting varied. So as I mentioned, lumped analysis, you can clearly observe, because the temperature of the entire sphere is at the same temperature, and you can also observe the increase in velocity. So that is acceleration. with respect to time. The temperature is also maintaining at the same value due to the Biot number less than zero point 0.1. So as soon as it reaches the wall, I have increased the time step size to 0.01 second. So now more amount of heat dissipation will take place. You can see the temperature of the ball is getting reduced. Initially it is at 1200 Kelvin. Now you can see orange color. So it is coming down and down. So now some part of heat is getting dissipated. You can see some fumes. It was coming normally to the room temperature. And for clear version, I'll just create local value for fluid such that it would be much more appealing to you. I just display wise, just looking about the display wise. Okay. So now we will check about the temperature. I'll just uncheck the velocity counters. We'll check the first temperature, how it is getting varied. So the buoyancy force and the net gravity force, as I have stated, it was increasing as due to the acceleration, net acceleration, or the difference between these two forces. So you can see the fumes. The ball temperatures are reducing, approaching 300. The water temperature is rising. So now we will go for velocity counters. This is the fluid region. Apply. Again, go to the animation, time step animation. Come back to original position. See the increase in velocity. This mesh is unrefined, so you're getting some velocities here, but it's not actually present. If you can refine the mesh in a perfect condition, you'll not see these things. So I'll just go to the last step. I'll stop it and I'll just show it to you. So this is kind of how the velocity would be distributed in the entire fluid of the water. Uh, Hope this video helped you in understanding quenching, dynamic mesh and lumped heat transfer. Please do subscribe the channel and encourage me in doing more number of videos. And if you have any comments or queries, please state in the comment section. Thank you.